Good evening, everybody, and welcome to tonight's Bakerian lecture. My name's Alex Halliday. I'm the Physical Secretary of the Royal Society, which means I'm physical, and I'm not non-virtual and all those good things. Just to explain that tonight's lecture will also be supported by a BSL interpreter and live speech-to-text. Tonight is a very special occasion for a number of reasons. It's always a special occasion, the Bakerian Medal and Lecture, but actually it's really great that we've got Andy, in particular, Andy Hopper, to give this lecture. The first time we've had a computer scientist actually getting this award. The lectureship was established through a bequest of £100 by Henry Baker, FRS, for an oration or discourse on such part of natural history or experimental philosophy at such time and in such manner as the President and Council of the Society for the time being shall please to order and appoint. So that's how we chose you, Andy. The lecture series began in 1775. Past winners have included last year's Andrea Ghez, John Pendry, Martin Rees, and further back in time, Fred Hoyle, Paul Dirac on the physical reality of quantum mechanics, James Chadwick on the neutron, Francis William Aston on mass spectrometry, Arthur Eddington on interstellar space, and William Bragg on X-rays. Ernest Rutherford gave the lecture twice, first in 1904 on radioactivity, and again, of course, in 1920 on the discovery of the nucleus of the atom. In fact, if you go back to the early days, Humphrey Davy gave the lecture 6 times, from 1806 to 1811, and then once more, but this time on electrochemistry in 1826. Such was the pace of discovery in those days around different elements, I guess. You may notice that nearly all these people were British Commonwealth citizens. 2 years ago, we agreed that the 3 Premier Awards, the Copley, Bakerian, and Croonian, should be opened up to the top individuals globally. So the competition's much tougher now than it was before, even though those people were not without their own merit. The Bakerian Medal and Lecture this year is awarded to Professor Andy Hopper, CBE, Fellow of the Royal Academy of Engineering and Fellow of the Royal Society, for his outstanding research in computer technology with significant economic impacts, in particular his work in computer networking, pervasive and sensor-driven computing, and using computers to ensure sustainability of the planet. Professor Hopper was presented with a medal and a gift of £10,000 at the Premier Awards dinner in October 2016, and portraits of all the Society's Premier medalists were commissioned and can be seen outside the lecture hall. Awards are about science and scientists. I think this is one of the only times, perhaps the first time, this award has gone to a computer scientist. Tonight's Bakerian lecture and lecturer make statements about the importance this field has now acquired. Andy Hopper is Professor of Computer Technology at the University of Cambridge, which is one of the Oxford spin-outs from a few years ago. He graduated with a degree in computer technology from the University of Swansea in 1974, before going on to study for a PhD in local area computer communication networks at Cambridge, which he completed in 1978. Andy was named by the Sunday Times as one of the 100 most influential Britons of the modern age. He has pursued careers in both academia and industry and has been head of department in Cambridge for more than a decade, a job he described to me as pretty easy, while simultaneously working for multinational industry companies and co-founding 13 spin-outs and startups, three of which floated on stock markets. In recent years, the companies he co-founded have received 5 Queen's Award for Enterprise. Andy is a Fellow of the Royal Academy of Engineering and the Royal Society. As I said before, he was made a CBE for services to the computer industry in 2007. He was President of the Institute of Engineering and Technology, 2012. He is recipient of the Royal Academy of Engineering McRobert Award 2013, and now the Royal Society Bakerian Medal. Today we are here to honour the science and the scientists, but it would be remiss of me not to mention Andy's considerable work for the Royal Society, most recently in helping to deliver our new cybersecurity report against huge odds. To give you some idea of how he operates, most Cambridge Academics get around by bike or public transport or perhaps a car. Andy doesn't have time for this and is the only FRS I know who has a landing strip in his back garden. He flew around the UK in his plane to get the Royal Society's cybersecurity report done on time. Thank you very much, Andy. Please join me in welcoming this year's Bakerian lecturer, Andy Hopper.
Well, don't believe any of that. That's just all tall stories. So, computing for the future of the planet. Actually, I stood here about 10 years ago and gave a lecture under that title. And so what I'm going to do today is reflect on the last 10 years, update, in effect, what I said in that lecture, and sort of talk about perhaps the next 10 years. So computing for the future of the planet is a vision, which I'll describe to you, which is then executed by a whole bunch of projects. And the projects are pretty practical. They build things to a reasonable level, which you can try and like or not like. And essentially all this research, I'm not aware of anything that wasn't funded by industrial gifts. So this is completely industry funded, but only through gifts, unrestricted funds, which make it possible to be perhaps a little more adventurous, dare I say, flamboyant on the one hand, and on the other hand, actually build stuff which is practical and you can demonstrate to somebody. Okay? So, this was the perspective 10 years ago, 9 years ago. My colleague, Andy Rice, was one of the principals, but others as well. And there is a reference on the bottom to the paper that followed. And there are 4 sections we identified at that time to think about this issue: optimal digital infrastructure, sense and optimize, predict and react, and then digital alternatives to physical activities. So that was then. What is now? This is now the same thing, but things have moved on, and I'm using slightly more colloquial expressions to describe what this might mean. So today, I think of optimal digital infrastructure as green computing. Sense and optimize as the other way around, computing for green. Predict and react has become assured computing, and digital alternatives to physical activities has become wealth and cyberspace. And I'll go through each one of these one at a time. And at the end, I'll give you some perspectives of where the world is going. So let's start off with the first one, green computing. So the world energy consumption in 2017 was about 150,000 terawatt hours. And the power sector, part of that, electricity generation, the primary consumption and energy consumption of that was 40% of that 150,000. And the electricity component is about 10% of that. And finally, within each sector, data center is about 2%, network is about 2%, PCs are also 2%, and then everything else, including mobiles, is about 4%. So while the initial number is very large, actually the ICT component is not enormous, but 10% of the electricity and growing, albeit other things are growing, is non-trivial. So I think it's worthwhile thinking it through. And hence green computing is concerned with minimizing the energy footprint of computers themselves. And so I'll report on the progress that's been done in this area, and in particular, starting off with data center design. So just in case you're not familiar, this is what they look like, and they're big. So the world has hundreds of millions of servers, maybe 200 million, something like that. And the investment in one of the centers, bottom left, is about £1 billion, pounds, dollars, whatever. And inside it's just full of racks of plumbing and computers at scale. So the energy efficiency of this consists of the energy you supply, well, not the energy efficiency, the energy use, and then how much is used for cooling and how much is used for computing. And I'm pleased to say that the design of data centers from a how much you use for cooling, and that sort of perspective has much improved in the last 10 years. It used to be that the overhead was about 100%. In other words, you use twice as much as the energy overall as you use for the computing part. And in many cases, this has improved now to something like a 15, 20, 25% overhead. Best practice is 15%. Techniques such as evaporative cooling have been used, lower voltage systems, 48-volt systems to supply the energy within the data center, so on. So this is pretty good progress. Some of the sort of details are trade secrets, but I think there is good progress. And the most recent developments, just to give you a little feel, are not only that there is evaporative cooling or 48-volt systems, but artificial intelligence, machine learning techniques are starting to be applied to augment the rule-based systems in operating a data center like this. And even though that only makes 1 or 2% difference, actually, remember, this is at huge scale and therefore it's important. So that's great. What about the computers themselves? Well, here are a couple of charts which show you server utilization. This is a cluster of about 10,000 from Google. And what you have on the x-axis is proportion of time, and on the vertical axis utilization. And the one on the left peaks the maximum utilization. About 30% of the computes are being used, of the servers are being used, whereas on the right it peaks at about 75%. And we're moving from the left to the right. I think the right is the best practice. So again, that's good. That's good. But we should be able to go beyond that in a number of ways. And here is the concept of energy proportional computing. In other words, you only use energy if there is some useful purpose to that computer doing its thing, and you switch all the other ones off. So beyond pushing it to the right, you try and switch off the things that you're not using. Now, this frightens people who run these things to death, but anyway, it can push up the efficiency. And this is made easier if some of the computing tasks that they're asked to perform are batch jobs, in other words, things that can be delayed. And this is particularly helpful to push the utilization up. And if you only had batch jobs, in other words, you could rearrange things fairly easily, that would be the best, 100% then. So that's good. What about storage? Well, here is the storage story from Facebook about a year ago, but I guess it's roughly right. So I think we have energy proportional storage, and what I'm showing here is the hierarchy of storage that Facebook used. So first of all, we have hot storage, and Google have 500, 600, 700 billion photos, and they promise to keep them forever. So, you know, this is huge scale stuff. Hot storage is read a lot, and they use replication across the data centers, across individual computers and the data centers, of about 3.5 copies of each photo, say, in order to deliver the performance that the user wants. But that data cools by over 500 over the first year, and so you can have a second level, warm storage, where the stretch factor is smaller, only about 2.5, and they start to migrate those photos and everything else after about a month. Then you have cold storage, which is read almost never, and here they have exactly this idea of switching things off. They have millions of low-cost drives. Only 1/15 are switched on at any one time, so they do exactly what I described in the storage domain. And here they have a stretch of about 1.4 copies of each thing. And then finally, they have very cold storage, read never, question mark, which is optical, so it's Blu-ray basically. And you push things out to keep your promise of never deleting anything. So that's pretty energy proportional, although I'm enough of a mathematician that if they say forever, so infinity times anything as small as you like is still infinity. It doesn't sound energy proportional to me. So there's an interesting question whether we should or should not delete things. What I suggest for the future is that we'll have something like hypothesis-driven storage, where if you've got a hypothesis how you might use the material, then you keep it. But if you don't even have any hypothesis, you might push it right into the tail and eventually delete it. Who knows? Let's move on back to the servers. and the concept of using renewable energy. So we're going to be using renewable energy for computing rather than conventional energy. Now, Barack Obama wrote a paper in Science in January entitled "The Irreversible Momentum of Clean Energy," in which he said that Google used 100% renewable energy for all their infrastructure. And that's done in two ways. There's direct use of renewable energy by putting your server farm close to your renewable energy source, and also by buying credits. So even though the electrons aren't renewable electrons, you're paying the supplier, you're paying a credit or money to the renewable energy supplier. So that's pretty good. That's a whole operation, as reported, and I heard it directly from Google. So that's really good. So can we go even further? Well, maybe we can chase renewable energy around the globe. After all, you can move computing around, not easily, but at least fiber is a miracle. Fiber is wonderful material. You can send things a long distance and you don't waste much energy at all. So the concept of chasing energy is an interesting one. Now, there's some delay, and the capacity may not be there, but why not chase it? And so please think of computing as a kind of virtual battery or a way of soaking up surplus energy, and particularly if you have jobs that can be delayed, that can be done. And finally, unusually cited data centers. So whether it's in a place where there's renewable energy, but you could never get the heat back, the electricity back because it's too far and use it as heat, or this rather interesting Microsoft project called Project Natick, which is a submersible data center. So it goes underwater. You see the rack over here. Cooling is not quite the issue it might be elsewhere. You've got water around it. Maybe as the waves go, you can power it. I think they're pushing the envelope. And illustrates the point of renewable energy, unusual places for server farms. It's a interesting and very happy story. So let me finish off this section with the last slide on technology perspective on these things and the trends going forward. So the trends are pretty good. The performance of hardware in terms of energy scalability is good. I had the good fortune of being involved in the original ARM technology, helping get that going. And when we were designing that, energy at the chip level had to be handled very carefully because we didn't have much money to design it, actually. But that's sorry, because we were clever about energy. No, actually it was the other. But anyway, it's a fact. And then workload trends are also, I think, helpful. If you take the machine learning, the very frequently discussed AI topic, well, the implementations tend to have a data set, some training phase, and some use phase. Well, the whole training phase can be delayed. And so if the world carries on in that direction, that's a very helpful thing. Okay, so that's green computing, and here are your take-homes for this section. Okay, 1, energy proportional computing. Useful purpose, actually quite difficult to measure, assess, and so on, rather than just convenience and everything on just in case you want to do it. And second take-home is the use of renewable energy. Could all the world's computing be done only using renewable energy, even directly, let alone by credits? Don't know, but I had the good fortune of supervising a PhD student on this topic. Anyway, so that's green computing. Let's move on. Now we're going to do computing for green. Turn it all around. So the idea of computing for green is to sense, model, and optimize everything on the planet. So you should be able to Google Earth in space, time. And as a computer engineer, computer scientist, how do we do it? I get all excited about that and say, oh, yeah, lovely, lovely. That's great. But the fundamental is to optimize resources once we're able to do it. And just by way of illustration, in a sustainability context, there are 2 trillion trees on the planet, and there are about 400 per person. Okay, so in other words, a number from a computer science point of view is completely tractable. So it's not completely absurd to have the idea of sensing, modeling, and optimizing everything on the planet. Now, in this section, I'll give you two examples of sensing and then reflect on them. One is an industrial example, which is where the sensing is very precise, very accurate, very engineered to give you facts from the sensing. It'll be location sensing. And the other one will be a mobile example where the sensing gives you very strong hints, but it's not quite in the same league. So let's start off with the industrial side, and I'm talking about products now. I'm not talking about research, I'm talking about products. So, indoor location. How much you do precise indoor location? Well, one way of doing it, the leading way of doing it, is you have a tag. It's a tag with a battery. It's a little mobile computer. It can chirp out some radio signal. It's ultra wideband for those who work in this area. You've got some receivers in the room, as shown. The whole thing is synchronized, and essentially by triangulation, multilateration, and angles of arrival, and all kinds of things, you can position this thing precisely, well, reasonably precisely. So you have an active tag. It's not a little RFID thing, and the accuracy is 30 centimeters, it says 15, but 15, 20, 25 centimeters in 3D, 95% of the time, and it's in real time. And the design of this product is such that it's scalable and can cover very large areas. So the product I am talking about is used in the car manufacturing sector. And here is a tool, electric tool, basically it's an electric screwdriver that costs $10,000, with the tag attached. So you can track it and essentially get the orientation as well in real time in a factory in a noisy environment, but using quite engineering, which gives me a headache, actually. It's so complex, but anyway, it works. So that's the important thing. And so here is how it's used. Here is a car plant in Germany. On the left, you have the cars going down the line. They're all tagged, so you know where they are. In the middle is person posing with a tool. I won't tell you what the brand is, but you can guess. And on the right, you have the virtual representation with some zones in different colors, and essentially you can program based on which zone a tool is in, switch it on, switch it off, reprogram it, actually at high precision. So you're tracking tools on a complex production line. You can automatically program those tools because you're facts rather than hints. And this reduces the number of, it makes for smarter manufacturing. However, for the purpose of this lecture, let me talk a little bit more about energy. Europe produces 15 million cars a year, and it's about 2,700 kilowatt hours per car. And this plant produces 300,000 cars a year. So it itself is quite big. And the final production, which relates to this, is about 20% of the factory. And a manufacturer in this situation was able to consolidate 11 production lines to 10 production lines to make exactly the same number of cars, in addition to making them in a smarter fashion. So if you actually work that through from an energy point of view, that's a saving of 7 million kilowatt hours. In money terms, it's 1 million euro, and a reasonable amount of CO2. Now, Obama, when he wrote his piece in Science in January, said, GM, General Motors, will reduce energy by 20% in their infrastructure. So I suggest to you, this is one of the ways companies, major companies, and this is, we're talking about the car sectors, humongous worldwide sector. This product is used to manufacture 5% of the world's cars, and I look forward to it doing the other 95%, please very much. And these are huge effects, not just on the efficiency of manufacturing, but on computing for green. So that was the industrial bit about products. Now let's go on to the little more consumer bit based on mobiles. And in order for those mobiles to be used, they have to work reasonably well and try and make the hints, well, they have to work, not work. And secondly, we try and improve the hints that they're giving us. And so I'm going to talk about this project called Device Analyzer, which again, my colleagues have done with aplomb, which is essentially a method of crowdsourcing data about mobiles in the Android world. So this is an application which people can choose to use, which monitors what's going on with the phone and can report back, including any sensing, but other things, has it got bad code in it or malware or whatever it is. Now, they've released this and they have about 30,000 contributors. So this is crowdsourcing from 30,000 what's happening to your phone. And from my point of view, can it be used as a good sensor platform? But it's crowdsourcing data, big data. And so they've actually done a very interesting thing. They've established what I think is best practice for data collection when you're trying to do this, some governance of big data. And what are the principles that they've used, and successfully, for example, are that it's never bundled, the application is never bundled, that there's a formal agreement with the University of Cambridge. If you agree to participate, you have a cooling off period, you have access to your own data, you get a reminder every month saying you're still part of this, it's all being reported. So it's got quite a substantive governance to it, and this took time, and if you're thinking of it from an academic point of view, it certainly delayed papers. But it was a very, very good thing and very important thing to do. So here is one of the interesting results. This is a graph which shows adoption of security patches. We have time along the bottom, and you have proportion of devices along the vertical axis. Forget the yellow on the left. Where it's all red, it's insecure, a new vulnerability has been reported. And as we go down, more and more in the crowdsource are saying, I've patched my phone, I'm no longer vulnerable. So we get a green secure. Yellow is, it's not clear one way or the other, it might be. Until the next vulnerability is reported, and up you go back to all red. So you see an awful lot of red. So keeping your phone up to date with respect to vulnerabilities is a very important thing. And if you're going to believe what your phone is doing, for example, it's not sending it to somebody else, you better be doing this. So we use this as a guidance for how we might reflect on big data in future, in particular for sensing. So let me carry on with this slide, which is from the Computing for the Future of the Planet point of view, what is the context for big data, which I know is a big subject. But here are three headings. First of all, on collection, we have to have transparency. Most people have no idea that as much data about them is being collected as is, and so I think making it clear is hugely important. We would not wish to have, I would not wish to have a GMO type of situation where there's tremendous resistance because people were not informed, they were then surprised. And if I might just say as a little commercial tickle, it's too bad that the majority of this data is ending up in Silicon Valley. Then secondly, there is who owns it. It's not clear. And I'd like to put forward to you that we have to have a category of social data, societal data, excuse me, which is where everybody owns it. It is declared that we share this data because it might be something about, CO2 levels, and it's just the bigger picture is more important than that single entity owning it, or health or whatever. So we have to have societal data. And finally, dilemmas. And the thought I'd like to leave with you is that technology will be part of the dilemma about who owns it, or what's the access, or am I losing my privacy, or whatever it is. don't lose sight that technology will be part of the solution. It will not be the same as we have today. And an example is reversible consent. If we had a mechanism which enabled somebody with some big data, say on that phone or whatever, contribution, say, I give my consent, but I'd like to take it back if I choose to do so, and I would like you to assure me that you will delete it wherever it went. Well, that would be a technological contribution which would help with the dilemma. There are plenty of other non-technical issues about it, I understand. Okay, so that's the computing for green. An industrial example, a crowdsourcing example, and so here are the take-homes for you from this section. We have precise sensing in an industrial sector, which is a high-intensity industrial sensor. So the leverage of that sensing in terms of energy, carbon footprint is huge. So that's good. Consumer sensing, on the other hand, can be deployed at huge scale, but doesn't give you facts, gives you strong hints. And then finally, new technologies will be part of the answer to the data governance dilemmas. So let me now move on to the third section, which is assured computing. So assured computing aims to improve the confidence we have in computer systems, particularly as societal dependence is increasing. They're in the loop of life. And there's much more automation happening, particularly with the advances in machine learning and artificial intelligence. And these are complex systems. So assured computing deals with this. Now, Alex mentioned something about flying, so can I do a little flying joke here? Okay, pilot joke. So aeroplane's quite complex, quite a lot of electronics. So what's the second most frequent thing that one pilot says to another? Well, it's, what's it doing now? But most of the time, it works very well. So what's the most common thing one pilot says to another? Well, it's wake up. So when considering these complex systems, we don't want any what's it doing now, and we don't want to take them for granted to the point that we have to say at some point, wake up, there's trouble at the mill, right? So assured computing is aimed at that. And there are technical challenges. Now, this is research going forward, basically, which relates to audit trails, transparency, what did it do, repeatability, the provenance throughout the whole system of what happened. As these things are more statistical, the bounding of errors, and in particular also self-healing. So that's once you find a fault, you somehow want it to fix itself rather than have somebody to attend to it. Security and privacy, I will skip that in this lecture, but surely it's important. But let me just say a couple of things about ethics. So I think ethics is now an important thing to start to understand as part of the design of complex computer systems which are in the loop of the planet. And let me give you two examples of what I have in mind. We need to establish some rules, ethical rules, about how an engineer designing these things operates. So one example might be that there shouldn't be any black boxes where you have inputs, things happen, you have outputs, apparently it works, but you don't quite know how. From the outside it looks okay, but you don't actually know. So it might be that. Another example might be that there will be no automatic decisions using machine intelligence of certain kinds. That's not allowed. So those are examples of how we have to start thinking about ethics. But let's get into the slightly more geeky bit. So let's talk about provenance in assured computing systems, which is the research that I've been doing with my colleagues in my group, and I'll report on a few things there. So the idea is we will keep a complete history of a piece of data and all its transformations, full stop. That's the core idea. And we want it to be a property of all computer systems forever from now on. Okay? Tall order, but that's the idea. And this provenance tool, or this provenance property, is a component of assured computing systems. And if you were to have such a thing, when data changes because it's wrong, it is possible to invalidate all the places it was used backwards and then recompute forwards, say, with the new data. And this can be on demand, or if you manage to do it, it can be automatic, which is precisely the self-healing property that I described. So it's a potential tool for self-healing. And so here are some uses. So that reversible consent I mentioned could be done if you had one of these things. You could say, I give my permission for this data, but it all keeps tools. I say, I change my mind, and it can all be undone. Of course, the hope is that the tool makes people comfortable to join in, and by the time they think about it, there is such benefit that they wouldn't dream of withdrawing. Transparency, well, this would help the concept of a flight data recorder for AI, or for anything actually, but since AI is popular, I'll say AI as many times as anybody wants. But you see the concept. You wouldn't design a plane right now to be unethical and everything without a flight data recorder. Well, why not have one of these things as part of the arsenal of computing as it is in the loop of the planet? And then validity. Now, I will not say fake and I will not say news, but were you to define those words, fake and news, and you had this sort of system at higher levels, you might have a shot at automatically working out an answer to the question, which I won't say, which is fake news. Okay? So, we've been at it for some years, many years. And here is a system architecture that we've put together. On the right are the labels that describe the basic levels of a computer system. Hardware, operating system, library, applications, a simplified model. And these sort of boxes represent different projects that we've prototyped, actual things that we've built. And I'll just give you a flavor of a couple of these. But I'm going to get into the more computer sciencey bit now. So you see, we're all over the place, but there is an architecture, there is thought in this. It's a systems view, it's not just a series of individual projects and that's it. So let's first of all talk about a thing that is observational provenance in user space. User space is application software. And so what we've been able to do at this level is capture and then query process provenance. Computers have processes inside them, and we've been able to record what they do. And we've been able to record it because we insert this code at load time between running programs and libraries. So we have persistent recording of all process library calls. And as I say, this is a background feature. It's a Unix system. It's just part of the system. So what, I hear you say? Well, here is an example of the answer to this so what. So say you're writing a paper on cats, and say it's the relation between cat color and popularity, and you have to comply with the EPS-SRC open data instructions. Well, you can do it by hand, but if you are running this sort of system, every line of the graph is traced back to the program that created it. You've got the trail, you've got all the links. Similarly with a photo, everything is there. So there is a complete audit trail, and so the compliance is automatic. You just hand it over. There it is. And beyond that, if science were to work like that, this might be an approach to erroneous data, or even, as occasionally happens, fake data. And it's automatic. It's in background mode. It just happens. It's a property of the computer system. Now, at this point, when I say provenance, all the computer science types have now woken up, because we like this provenance of provenance of provenance of provenance. It's called recursion, and everybody goes, oh, I like this sort of stuff. And everybody else says he's lost the plot. This man is just completely useless. So this is just one slide. Just bear with me, okay? So provenance of provenance is the answer to the question, how do you know that your provenance is correct and hasn't been wrecked by some intrusion, some malicious software, some falsification, some circumvention of the log, so that it's not true. So here we've got a provenance support for kernel computations, and essentially it's probes. So at the lowest level in the computer, we've got probes which can observe and also things report out what's been happening. And quite a lot of work has been put in to make the performance of this reasonable. And what we're observing is the pattern of I/O transfers in the system, rather than just having crypto security barriers. And so we're going to use the pattern of I/O transfers as the fingerprint, if you like, rather than traditional barrier approach. But we still have to have a trusted zone, but the trusted zone can be quite small, and it includes actually special instructions, which Intel, for example, provide, so that it can be rather small, and it's got hardware component in it, which is intrinsically harder to attack. It still can be done, but if you're using hardware, that's a good start. And the deepest thing I'm going to say is we're also going to have a proof of work function in this, so that it's not only the I/O patterns, but the measurement of how much CPU power was used, how many CPU cycles were used to perform a certain thing is part of the authentication that this is a correct thing. Think of it as cryptographic puzzles being thrown at the problem, which have no back doors and can be solved, but it takes a certain amount of computer power to solve them. So that's the concept. And so we end up with provenance of provenance, which has a much reduced security enclave that has to be trusted, and we can avoid falsification and circumvention. Okay, all the techies now back to sleep, and everybody else, you can start concentrating again. Well, that's what we do for a living, day by day, and they're very good. So what's the take home from this section about assured computing? We need assured computing. Secondly, there's plenty of room of innovation. I can see companies, new companies, other companies using this stuff. It's right in the mainstream of innovation. And then finally, I'll just go back to this ethical dimension. Assured computing as a component where we feel comfortable that an ethical dimension is done and assurances against that ethical dimension in addition to all the technical things I've talked about. So let's now go on to the last section. So everybody now start concentrating again and talk about wealth and cyberspace. Wealth and cyberspace. So I'm aiming this at low-income countries, sub-Saharan Africa or wherever, low-income countries. And I'm thinking of a situation, how can they have their cake and eat it without having the footprint as bad as ours? And so this is Kampala, and my suggestion is that, obvious suggestion, low-income countries can use technology to bypass intermediate development steps. So they have to, and as a computing perspective, they need to keep deploying the latest digital infrastructures. But please note, they can take advantage of global technology platforms for nothing. And you might call this wealth by proxy. You've got wealth in the real cash sense. You've got wealth in having a family and happiness. But you've also got wealth by proxy. And so let me just remind you what wealth by proxy is. GPS is wealth by proxy. You're not paying for GPS. And they're not paying for GPS. Computing power, you can get free computing power. They can get free computing power. Storage, free storage. They can have free storage. In a different dimension, massive online teaching and more bespoke teaching available free. Messaging, WhatsApp, remote desktops such as real VNC supplies, or even things like Uber, where it's not just that they can use GPS and so on. Here is a Nairobi story I heard the other day. Why is it that people like Uber in Nairobi? Well, because there's no cash. And if you've got no cash, there's nothing a policeman can do to make you pay the bribe. So it's real, my colleague came back from the day before yesterday and told me this story. So not only is there sort of free technology, but there's an effect. And actually, I won't talk about it, but there's a line about why corruption may be improved with these sort of technology. Now, a very important thing is not to evangelize, not to be colonial about it. You have to go there and you have to do something. So we've had some projects in sub-Saharan Africa, in particular Rwanda. And in Rwanda, we had the good fortune of coming to a deal with the operator, so we collected all traffic on their mobile system for a week, everything. Disks went there, sucked it up, came back, all through the ethical committee and so on. And just one result I'll show you. Here is a graph of top handset brands by bytes and by users, and the top right is a brand called Techno, which none of us have heard about. So the low-cost brands dominate. And so I suspect the updates aren't happening. So the digital infrastructure might be a bit creaky. But let's start thinking. So one of the interesting things that's currently happening in Rwanda is drug delivery trials by drone. So there's a drone dropping something. So if you can do that, just think how you can design the medical service in that country. You can have a central place where the quality is kept up, the temperature is right. You can then deliver within an hour to any part of the country. The way you think of medical infrastructure just completely changes. And there's a second component which they have an advantage, which is this. Here, if you want to fly a drone, because the airspace is very complex, it has to be line of sight. Well, this doesn't have to be line of sight because they don't have the airspace complexity that we do, so they can just go ahead and get on with it. And they're building a drone port and will be one of the leading places for drones. I personally think they're the Singapore of Africa. So that's existing, but let's just dream a little bit. A couple more things. Here is a potential scenario. Actually, the picture is of California Valley, and it's a picture. What Google have done is taken high-resolution pictures and worked out the surface of everything, including the roofs, and provide a free service which says how much sun falls on that roof and how much energy you could get if you put a photovoltaic on it. Why not provide this for the urban areas in sub-Saharan Africa? They don't have the maps, unfortunately. What about rural areas in those countries? Well, they will probably have lots of mobile phones, better ones in the future. So think of watching plants grow, literally watching plants grow. And what would be the proxy services one could provide that would support that? So to summarize, mid and low-income countries can take advantage of the digital infrastructure and global technology platforms, and we can provide a new form of aid. It's a bad word in some senses, aid, I don't like it, but nevertheless, which is stuff we make available for free. For example, why not provide those maps or a maintenance and security vulnerability service for free for those mobiles, or other bespoke services which do the agronomy or whatever. But we can't do it without empowering the individuals, because after all, it's their world, they have to do it. And fortunately, the computer science clusters are doing quite well, so in terms of the technology, they're starting to have the capacity. So what's the take-home? Well, the take-home for this section is that low-income countries can bypass intermediate steps of development, in their development, that we can have wealth by proxy at scale, and there was a suggestion for a new form of aid. So let me now finish off with some concluding remarks. So 10 years ago, when this was described, the academic community thought it was completely weird, beyond the pale. Remember, iPhone only came in 2007, so it was a different world, but whatever. And the industrial people said, oh, it's too far out. And I've never been so surprised for things to turn around, and green computing and computing for green are completely mainstream right now, right? Everybody's doing it, academically, industrially. So it's been tremendous. And I very much hope that the next 10 years are equally productive. Say on the assured computing, which think of it as a kind of pacemaker for the planet. We really need it, it mustn't go. Or this whole wealth and cyberspace, where low-income countries may benefit from tremendous development and really value this wealth by proxy. I don't know. That's the next 10 years. But I hope I'm pleasantly surprised about the adoption. Well, putting it in a slightly different way, use as much computing as possible, sense and optimize all resources, be careful because it might bite you. And I'm still surprised that people who work in my sort of line end up having their stuff used by everybody on the planet. It's in everybody's pocket, and I just don't quite understand how that works, but it's a miracle and it's tremendous. So the reach is outstanding. Here is the crew that does it. I'm tempted to say this is an ancient photo of us looking for the next vision, but actually it's the 20th anniversary of our open source weather station. And of course, they've done all the work, and I'm just the mouthpiece, and they're a tremendous crew, so I thank them all very much. Thank you very much indeed.
Thank you, Andy. I think you'd agree that was an amazing lecture. We've got a few minutes, 10 minutes for questions if people would like to ask any questions. We've got roving mics. I have to say together. Roving mics, so there should be a couple of them around. If you have a question, perhaps you could make it fairly succinct, because we've only got 10 minutes. Just don't say too much about yourself, mainly get to the point of the question, if that's okay. But any questions? Yes, we've got one here at the front.
Thanks for a wonderful lecture, Andy. I just wanted to ask you a bit more about the provenance idea. If you are tracking what happens to the data, and suppose you want to be able to retract it in the way that you were saying you'd like users to be able to retract it, because sometimes the data has gone through many transformations and is unrecognizable. Maybe a good example would be a parameters in a machine learning program where many people's data have all been confounded, and now one person wants to retract their data. So the computation to unpick the contribution of that one person could be very expensive, or else throwing the whole system away could be expensive in a different way. What's your view about how one would handle that?
Well, the general problem is very difficult and maybe impossible, but the specific problem, for example, MapReduce, we have a prototype that keeps tags of all operations going through MapReduce is the major technique of mapping large data sets through an intermediate format into smaller data sets. And up till now, it's been done without a tag, whereas now it got it at reasonable performance. And so at least for that component of the infrastructure, which is the biggest one, at performance loss of about 10 to 50%, depending how you count, so not too bad, we've been able to show that. So in that particular area, great guns. More generally, it's a little bit ambitious. I agree with you, and I'm sure there's tremendous research here, because whether it's, you decide you're definitely not going to keep it and actually keep a note of that, you notarize it, or the converse, you deal with the explosion in some way or another, or you say ethically you can't do it this way because we've got to keep track, and that's that. So you're outside the bounds of either regulation or best practice or standards or whatever it is, or being able to describe it to your friends.
My question. Yes, got one.
Hello, thank you very much, Andy. This is a layman's question. Going back to your invalidate data backward, or rephrasing that, it is the going backwards. What I have thoughts about is historical archives, because some of it is very delicate, and you're trying to gather up crumbs of information and make sense of it. And if it starts getting sort of invalidated, it then makes a mess of historical archiving. and wondered your thoughts.
Well, at the moment we can't even begin to do it because there aren't properties like that at all. So this is a system which proposal and some, it's not demonstrations because they're actual systems you can try, which at least gives you the tool to then decide whether you want to do it or not. There is an argument the other way, which I understand. What is public anyway, and should you be able to withdraw it? And it might say, well, you didn't like that photo, you want to replace it, but that would be to unwind history, therefore you shouldn't be able to do it. I do understand, but I'm just trying to give the tools so that you can even begin to be able to do it, let alone it's a black box, it does something, and it's unexpected result, and there's nothing you can do about it.
Thank you.
I have a question over here.
Hi. On the topic of crowdsourcing data, who do you think should be responsible? The government or private entities or public entities?
Yeah, well, in my head I have a hierarchy. So there's societal data, which I think we should just declare as being societal regulation. Next level up might be something that is done by a business cluster. In networks, computer networks, wireless networks, there are agreements on standardization of how things interoperate. So a cluster, say for medical purposes or whatever, of businesses could agree some standards and start exchanging those. So one is sort of more societal, the other one is a little more business. I don't think I can help you with a precise answer because this is evolving, but I will say again that technology will help. You tell me what would be the most wacky rule you'd like to apply, and I'll tell you whether there's a chance in hell of building the technology without having to turn the world upside down.
Yes, there's a question there towards the back. Your microphone. You need to put your hand right up. There we go. Thank you.
Hello. You said low-income countries can take advantage of technological development and bypass intermediate development of technological products. But currently, a lot of technological products are expensive, and because of the value of their currency, so it gets more expensive there. So do you think low-income countries can increase their technological impact in the world and get to what you can call a standard level of technological development?
Yeah, well, I agree, there are basic economic factors and there is some level of money required in order to put in the infrastructure. Fortunately, the cost of digital infrastructure in relation to the wealth by proxy, I would argue, is good. You're getting something valuable. And also I've been quite impressed that, notwithstanding that you still have to pay for it, the most popular thing that was on that mobile is WhatsApp, right, in Rwanda. Everybody messaging, it's individual messaging, so it's quite popular. So, understanding that, participating with my colleagues in, whether it's Rwanda, Bakerian University, or in Nairobi, or whatever, I get the feel that there is an opportunity to at least make some headway. And I would hope that these digital technologies will, because remember what I said was you can then use them to optimize water, you can use them to perhaps deal with charcoal being burnt and polluting because that's their form of energy or whatever the local situation demands. And at least I've got a story, whereas and that's better than no story.
Yep, there's one more over there.
Hi, Andy. So you touched on...
Where are you? Who are you? Oh, there you are, yeah.
So you touched on what is the system doing and helping people to understand the black box that is the system sometimes. How much of that do you think needs to come from writing better software and visualizations which educate people in that? And how much needs to come from sort of grassroots education and sort of making maybe understanding, computing the next, the ability to read and write, basically?
Well, both things are important, and of course this is generation-driven. I'm at the back end of my career, and I haven't got a clue what's going on with the young generation. My wonderful children who are here can educate me on that. And they do have a different mindset. They do have computational thinking, and unfortunately, at least in this country, we're now making progress again, not least because Raspberry Pi and other things like that to do that. But I can only be philosophical. What I can say is this. Nobody would have predicted Facebook was going to be this popular. And if you had made a proposal for Facebook to Google, they would have said, get lost. It didn't come out of Google, is my point, right? So innovation and the way we change our lives will continue to change, at the same pace. In 10 years' time, it'll be different. And I take a very positive view of that. It sort of helps with a human need.
We need to wrap this up now, I'm afraid. But in closing, I'd just like to say thank you hugely to Andy. But also I'd like to say that I think it's a sign of the times that computer science and technology and the internet, etc., are being talked about in these lectures. Computer science and information is now a bigger subject in this country, as judged by the ref and all that stuff, than physics or chemistry. And it's a massively important subject for the future. And it's great to hear a lecturer come up in such a wonderful way and explain to us in a visionary sense what's going to happen in the future, but also give us a sense of sort of humor as well and excitement about it.
What's it doing now? Yeah. What are you doing now?
So Andy, thank you very, very much. It's great that you won this award, richly deserved, but also it's great that you gave such a stunning lecture, and thank you very much.
Thank you very much. Thank you very much. Thank you.